Today's lesson is on the topic 7 review. Mason plays a game by flipping 2 fair coins. He wins the game if both coins land facing heads up. If Mason plays 200 times, how many times should he expect to win? Take a second to copy down the question. The first thing I'm going to do is determine the probability that he wins. In order to win, he needs both coins to land heads up. So I'm first determine how many total outcomes there are. This is for the first coin and the second coin. For the first coin, there's 2 options, heads or tails. For the second coin, there's still 2 options, heads or tails. To figure out the total outcomes, I'm going to multiply these numbers. 2 times 2 is 4. So that's how many total outcomes there are. So that's going to be the denominator of my fraction. Now to determine how many times there are both coins land heads up, I'm going to create a tree diagram. For my first coin, I can have heads or tails. For my second one, it could be heads or tails. For my second one, if it's tails, it could be heads or tails. For both coins to land heads up, there's only one option, heads and heads. So it's a 1 out of 4. That's the probability that both coins land facing heads up. But now Mason plays 200 times. So I'm going to create a proportion, x over 200. And I'm just going to cross multiply and solve. 1 times 200 gives me 200. 4 times x is equal to 4x. I can divide both sides by 4. 200 divided by 4 is equal to 50. So we have 50 equals x. So that means that Mason can expect to win 50 times. Jessica records the number of winners at the Dunk-A-Teacher booth at the town fair as shown in the table. Based on the results, if there are 750 contestants on Monday, how many should Jessica expect to dunk a teacher? Take a second to copy down the question. Now, this problem says based on the results. So I'm going to find the experimental probability. Now, I'm going to find the experimental probability for the whole entire 3 days. So I'm going to find the total number of contestants and the total number of winners. To find the total number of contestants, I'm going to add up those 3 numbers. 215 plus 417 plus 368 is equal to 1,000. So there's a total of 1,000 contestants. Now I'm going to determine the total number of winners. 27 plus 54 plus 39 is equal to 120. So there's a total of 120 winners. So I'm going to write my experimental probability that somebody will win. There were 120 winners over the 1,000 times the experiment was conducted. Now I need to determine how many people win if 750 contestants play on Monday. So I'm going to set up another proportion and make it x over 750. I'm going to cross multiply 120 times 750 is equal to 90,000 equals 1,000 times x is just 1,000x. I'm going to divide both sides by 1,000. 90,000 divided by 1,000 is equal to 90. So Jessica can expect there to be 90 winners if 750 contestants play on Monday. Develop a probability model for rolling a cube with faces numbered 1 to 6. Take a second to copy down the question. A probability model has two things. The first thing is the sample space. To list out the sample space, we could just put an S, and then we're going to have our brackets showing the sample space. I'm going to list every possible outcome that can come from rolling this cube. My outcomes are 1, 2, 3, 4, 5, and 6. That is my sample space. A probability model has a second part where you list the probability for every event in the sample space. So I'm going to have to find the probability of a 1, probability of a 2, probability of rolling a 3, probability of rolling a 4, probability of rolling a 5, and the probability of rolling a 6. I'm going to have to find all 6 of these probabilities. The probability of rolling a 1 is 1 out of 6. Probability of rolling a 2 is also 1 out of 6. Probability of rolling a 3 is 1 out of 6. Probability of a 4 is 1 out of 6. Probability of a 5 is 1 out of 6. And the probability of a 6 is 1 out of 6. Now, if I want to make sure that I did it correctly, I can add up all my probabilities. Since all of my probabilities have a denominator of 6, I know my denominator will be 6. Now I can just add my numerators. I have 1, 2, 3, 4, 5, and 6. So I have 6 out of 6, which equals to 1. So since I got a 1, that means that it would be 100%, so it's showing all the possible outcomes, so I know I did it correctly. A restaurant offers 3 types of wraps: chicken, veggie, and turkey. They offer 3 drinks: milk, water, iced tea. And they offer 3 snacks: fruit, chips, and jello. How many possible lunches can be made with 1 wrap, 1 drink, and 1 snack? Create a tree diagram to show the options. Take a second to copy down the question. So first, to determine the total number of outcomes, I'm going to have to determine how many different events there are. We have a wrap, drink, and snack. So there's 3 different options. We have the wrap, the drink, and the snack. Now I'm going to determine how many different wraps there are. There's 3 types of wraps. Now I'm going to determine how many drinks there are. We have 3 options for drink. Now I'm going to determine how many snack options there are. There are 3 options for snack. I'm going to take all of these numbers and I'm going to multiply them to determine the total number of possible outcomes. 3 times 3 times 3 is 27. So there's a total of 27 possible outcomes. Now I'm going to make a tree diagram. To make a tree diagram, I'm just going to start with the first option that you can receive from this restaurant, which is the wrap. So for the wrap, there's 3 options. We can have chicken, veggie, or turkey. Now if you get chicken, from my drink option, there's still 3 options. So we're going to have 3 options come from there. We can have milk, water, or iced tea. If we went with the veggie, we still have 3 drinks options: milk, water, or iced tea. And if we went with the turkey wrap, we would still have 3 drink options: milk, water, and iced tea. So this covers the wrap, this covers the drink, but now I also have to cover my snack options. If I have chicken and then milk, there's 3 drink options, snack options that I can have. I can have fruit, chips, or Jell-O. If I have chicken but I have water, I still have 3 snack options: fruit, chips, or Jell-O. Same thing with iced tea. There'd be 3 snack options: fruit, chips, or Jell-O. Same thing with all of my wrap and drink options. There's 3 snack options: fruit, chips, or Jell-O. So I would just continue drawing that down from each option. When you're drawing a tree diagram, again, all of the branches don't have to be the same size. If you need to draw them differently so that you can fit everything, that's okay. So from every drink option, I have my fruit, chips, or Jell-O coming down. Now if I want to make sure that I have all 27 possible outcomes, I can count the very last branches from every single option. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So I have all 27 options listed. You play a game where you spin 2 spinners. One spinner has letters A, B, C, D, and the other spinner has numbers 1, 2, 3, 4. What is the probability that the 2 pointers will land on an odd number and the letter C? Take a second to copy down the question. To determine the probability, I'm just going to first determine my total number of outcomes. There are 2 spinners, so I have my first spinner and my second spinner. My first spinner has 4 options, and my second spinner also has 4 options. So I'm going to multiply those 2 numbers. 4 times 4 is 16, so that would be my total number of possible outcomes. So I know my denominator is going to be 16. When you have 2 events, I need to determine how many events there are that have an odd number and the letter C. When you have 2 events, the easiest thing to do is to create a table. I'm going to have my spinner 1 on top, so that's A, B, C, and D. The second spinner has numbers 1, 2, 3, and 4. A table is the easiest way to see every possible outcome. Now, since I'm just looking for the probability, I do not need to fill in every part of the table. I'm just going to see where I have an odd number and the letter C. I know it's going to have to fall in here because that's the only option where I have a letter C. And an odd number can be here or here. So there's only 2 possible outcomes. So it's 2 out of 16. 2 out of 16, and I can reduce that to be 1 out of 8. So the probability that you get an odd number in the letter C is 1 out of 8. And the last problem. At a school, 30% of students buy lunch and the rest bring lunch from home. Using the numbers 0 to 9, which number should be assigned to buy lunch and which should be assigned to bring lunch from home? Take a second to copy down that part of the problem. So for this problem, we have two options. Students either buy lunch or students bring lunch from home. They say 30% of students buy lunch, and we're using the numbers 0 to 9. Since the numbers 0 to 9, there's 10 options. 30% of those numbers would be three numbers, so it would be 0 to 2, because that would be the numbers 0, 1, and 2, and that's 30%. So that means students that bring lunch would be the rest, which would be 3 to 9. So that would be the 7 numbers to make up the other 70%. If you wanted to use other numbers, it's okay, as long as buying lunch had 3 numbers, or 30%, and the rest of them were for bringing lunch. It's just always easier to keep it with numbers close together, so it's easier to do the simulation like we're going to do in the next part. Using the above information, based on the simulation below, what is the probability that at least 3 of the next 4 students buy lunch? So for this part, I'm going to go through and see how many total simulations there were. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I know my denominator is going to be 12. We need at least 3 of the next 4 students to buy lunch. So that means it could be 3 or more. So it could be 3 or all 4 of them. So we need 3 or more numbers to be either 0, 1, or 2 for students who buy lunch. In this one, 4780, that's no good. 3981, that's no good. 3418, that's no good. 3290, no good. 2280, that's good because this is buy lunch, buy lunch, buy lunch. So that works out. 3897, that's no good. 1234, that's no good. 9021, we have 1, 2, 3 students. So those 3 students buy lunch. So that works. 3489, that's no good. 9820, that's no good. 1288, that's no good. 7771, that's no good. So I just look to see how many checks I have. I have 1, 2. So it'd be 2 out of 12. Or I can simplify that to be 1 over 6. So based off of the simulation, the probability that at least 3 of the next 4 students buy lunch is 1 out of 6.